Uh, we're starting in the last paper for today. This is coming again from NXP. The topic of today's presentation now is reset verification. And the title is Achieving More Qualified Reset Verification Results with Intelligent Reset Domain Crossings Detection for two non-resettable registers and POPs. Coming from authors Jagadeesh, Ambati, Inayat, Atul, Sharma, Sulabh, Kumar, Khare. The floor is yours, guys, and we'll reach later for the questions.
Hi everyone, myself Jagadeesh, an R&D engineer at Siemens EDA. I, along with my co-workers Sulabh Kumar Khare and Atul Sharma from Siemens EDA and Inayat from NXP Semiconductors, are going to present a systematic methodology as part of static analysis called skip-NRR analysis, which helps in achieving more qualified reset verification results with intelligent reset domain crossing detection to non-resettable registers or flops. Without further ado, let's start our presentation. These are the contents of our paper. We will be discussing briefly about reset domain crossings, NRR and RDC to NRR, safe RDC to NRR, and what is skip-NRR based RDC analysis, along with some design scenarios. We will also be discussing about effect on accuracy and noise in the results that we have after reset verification, along with the case study, and we have a conclusion. Moving to the next slide. Now let us discuss briefly about reset domain crossings, RDC. So complex designs and SOCs have multiple asynchronous resets, which split the chip into multiple reset domains. Each domain is reset independently with respect to other reset domains. So the asynchronous reset session at transmitting flop domain TX, and that causes a data change at receiving flop domain RX. So these data transfer between the reset domains are termed as reset domain crossings or RDCs. So this asynchronous event may occur in the setup and hold time of the receiving flop domain, which may induce metastability in the receiving flop. So these metastability issues are critical because they might cause design failures. And we capture these issues using reset verification. Now let's move to the next slide. NRR and RDC to NRR. So NRR is a non-resettable register which doesn't have a reset pin. So if a signal crosses from reset domains from an asynchronous reset source to a non-resettable destination in the same clock domain, the sequential element without a reset is considered in its own reset domain, making the crossing an RDC. Okay, so now let's take a look at the time diagram. Here at the positive edge of the clock, the TX output is reset, which might cause a data change at the setup and hold time of the clock domain of NRR outputs. This might cause a metastability issue. So these metastability issues are critical and they need to be addressed. Going to the next part. What is safe RDC to NRR? So these RDCs to NRR might not have metastability issues sometimes if a flop exists after the NRR flop, which is having the same reset domain as that of the transmitting flop TX. So for this to be safe, there is a condition that needs to be satisfied, that the reset signal should be long enough to suppress the metastability at F1. Now let's see how this metastability is suppressed at F1. So here when the TX is reset, it might generate metastability at NRR because of its value being changed at setup or hold time of this clock domain. So when this metastability is propagated to F1, let us say if F1 has a reset which is long enough that it kept the F1 in reset state until the metastability is propagated to F1. So now the metastability is blocked here. So the metastability will not propagate further. So then this crossing will become a safe crossing. So we provided this condition that reset connected to F1 is same as TX and it is long enough until the metastability is propagated to F1. It keeps the F1 in reset state, the metastability will be blocked. Moving to the next part. What does skip-NRR based RDC analysis do? So the skip-NRR based RDC analysis identifies multiple fanouts of NRR RX skipping intermediate NRR flops within a specified depth. So these help us to detect the crossings with all safe fanouts and report them as safe crossings. This can also help us to detect crossings with fanouts in different reset domains, as in different reset domain with respect to the transmitting flop TX, and helps us to capture all the existing safe and unsafe fanouts. So this gives us a clearer picture of actual safe and unsafe RDCs in the design, along with the safe and unsafe paths associated with those crossings. Moving to the next part, let us discuss some design scenarios. So in this design scenario, we have a crossing from TX to NRR1, since NRR1 is in its own reset order. So without this methodology, with the reset verification, we report this crossing as a byte. Now, let us say with this methodology, we are analyzing the fan outs. So now let's take a look at the fan out of NRR1. Let's go to a depth of 1. So at a depth of 1, we have NRR2, which doesn't have any reset. So the metastability generated at NRR1 will be propagated to NRR2. So the metastability still exists here and is not blocked here. And now consider a depth 2. So here at Q1, it is having a reset 1, same as the transmitting flop TX. So if we consider that reset 1 is long enough until the metastability is propagated to Q1, as Q1 is already at reset state, the metastability will be blocked at Q1, making this crossing TX to NRR1 a safe crossing. So this will be identified using the methodology skip NRR based RDC analysis. So this will help user to reduce his efforts in analyzing these false crossings from TX to NRR1, provided we have safe fan out paths. Here, the depth which we mentioned is defined as a skip depth, which means it is the specified depth of how many intermediate NRRs to be skipped. So moving to the next slide, design scenario 2. So here, similar to the first design scenario, we have a crossing from TX to NRR1, whereas here we have different fan outs. So here we have 3 fan out paths from NRR1 to Q1, Q2, and Q3 through NRR2. So considering the same explanation as before, we can say that this path from NRR1 to Q1 through NRR2 is safe, since Q1 is connected to same reset 1. But the paths from NRR2 to Q2 and NRR2 to Q3 are not safe, since they are connected to different reset domains, as they might not keep Q2 and Q3 in the reset state when the metastability reaches them. So this makes the fan out path to Q1 from NRR1 as safe fan out, since it has same reset 1. The fan out path to Q2 is unsafe, since it has reset domain reset 2. The fan out path Q3 is also unsafe, since it has reset domain reset 3. So without the skip NRR analysis, we still report this as a violation, but with this methodology, we can also give this information to the user that we have these particular safe and unsafe paths, and we can provide them the info of where the metastability actually exists. Moving to the next design scenario 3. Here also we have the crossing from TX to NRR1. So without a skip NRR analysis, we don't investigate the fan outs of this crossing. So we directly report it as a violation. So now let us take a look at the fan out path. So here NRR1 has fan out to NRR2, which has fan out to NRR3, and we have end fan out to Q1. And Q1's output is going to NRR2 through a combo logic. So we have a loop here. So let us consider a depth of 1. So at depth 1, we have NRR2, which doesn't have any reset. So the metastability reached here will not be blocked, since it is not in the reset state, and will be propagated further. Now let us consider the depth 2. Here at NRR3, since it also doesn't have any reset, the metastability will propagate it further. Now let us consider the depth 3. Here at Q1, it has a reset. Let us say the reset is same as the reset of the transmitting clock TX, and it is reset 1. And let us consider that it is long enough that the reset will keep Q1 in reset state until the metastability reaches Q1. So here the metastability will be blocked, since reset 1 already keeps Q1 in reset state. So even after some, even if there is some metastability, it will become stable after certain cycles in this loop. So this crossing from TX to NRR1 will be safe. Now let us consider that Q1 has a different reset domain reset. Now the metastability might not be blocked at Q1, since reset 2 might not reset Q1 when the metastability reaches here. So this metastability will be propagated further, and we cannot say that this signal will be stable even after infinite cycles because we have a different reset rate. So this will become an unsafe path and it will make the crossing an unsafe crossing. So with the skip and error analysis, we will report this crossing as a violation when the depth is less than 3. We report this as a safe crossing when the depth is greater than or equal to 3, provided Q1 is having the same reset 1 as that of TX. And with a depth greater than or equal to 3, we report it as a violation if the reset is at Q1 is different with respect to this transmitting clock TX. Moving to the next slide. So what is the effect of this methodology on accuracy and noise? Considering the application of proposed analysis on design scenarios discussed, we came to the following conclusion. For noise reduction, all the invalid violations which were actually a safe crossings in which the metastability is blocked are identified using this methodology, and we are able to detect the actual safe crossings to NRR and reduce the noise and ripples. This helps the user to reduce the manual effort in analyzing those false crossings. So moving to the improved accuracy. With this methodology or proposed analysis, we are able to detect the safe crossings which were not actual violations, and we are able to capture the unsafe nodes of NRR crossing and thereby identifying the actual paths not free from metastability, which we can say are effective RTC paths. So making these two information will make the result more accurate, and this helps the user to reduce the effort in analyzing and fixing the RDC issues which are unsafe more accurately and effortlessly. Moving to the next part, let us now take a look at some real-time designs on which this methodology or proposed analysis applied. These tables capture the percentage decrease in violation count with respect to the skip and RR depth applied on some NXP designs. So let us take a look at the design one, which has total RDC and RR violations of around 3200K. Here, with an increase in depth, the number of total safe paths that are captured are increasing, and the percentage decrease of unsafe paths is increasing. So let us go through the depths. So at depth 1, we are able to identify 148K safe paths of total violations which were actually safe and were reported unsafe without this methodology. So there is 4.49% decrease in the unsafe paths count. So now let's take a look at depth 5. So we are able to capture 201K safe paths which are actually reported as unsafe violations without this methodology, and we are able to decrease the percentage by 6.17% of unsafe paths. With the skip depth 10, we are able to capture 315K actual safe paths which were reported unsafe without this methodology, making the decrease in unsafe path percentage by 10.04. Now let's take a look at the design 2 with the total RDC and RR violations of around 1320K. So with the skip depth 2, we are able to capture 29K safe paths which reduce the unsafe paths count by 2.24%. And with the skip depth 5, we are able to capture actual safe paths which are reported as unsafe without this methodology, and we are able to reduce the unsafe paths percentage by 5.82%. So typically with a higher skip depth value, more unsafe paths turn into safe paths. Moving to the conclusion. So this automatic technique helps us improve quality of static RDC analysis results and reduces the time required to identify actual RDC issues to NRR. It also helps us to identify only the relevant unsafe RDC paths and helps us or users to focus on verifying them effectively. Several scenarios showcased in this paper ensure that no critical path is missed and no false crossings are reported. So the validation of these methodologies or proposed analysis on real-time designs and SOCs confirm that this technique is practical and must be applied on modern designs as part of static RDC analysis. That's all. Thank you, everyone.
Hi, Sai. Hi, Atul. Thanks for your nice presentation.
Sure.
Yeah, I think I have a few questions from the chat. Let me report you. First of all, I think depth changes, how well they're determined. I know you have experimented multiple depths, but what was the ideal depth for a given design? How was it determined, and what is the trade-off with run times? Because you're saving the debug time versus what is the impact on runtime.
Sure. So as the depth increases, it all depends how many fan-outs we have. So for a specific design, it is quite possible that we have lesser fan-out as we skip the NRR flops. In that case, the runtime impact won't be too much. But if, let's say, right after skipping the one flop or two flop, if we have many fan-outs to that, it may increase the runtime drastically. So that's the impact on the runtime. As a recommendation, we should skip at least the depth 2, but it all depends on the respective design. And then it's basically the design house's call whether they want to skip the depth for level 2, level 3 or more, because they have to make sure that it will not lead to the high power dissipation as well. So just in case if the number of fan-outs are too much for the depth 2 itself, and then you specify the depth 3, the lot of power dissipation will happen because of the metastability propagation, and there could be the problem to the chip. So that's that call has to be taken on the design basis.
Okay. The other question is it being done mostly from a flat verification perspective? What happens if the fan-outs happen to the top-level ports or black box ports? How do you recommend verifying more from a hierarchical standpoint for skip reset?
Yeah, so we do preserve the skip depth, and we do report the basically RDCs at the output port level as well. So let's say if you are running in the hierarchical model, the HDM flow, and you have specified the depth as 2, but right after skipping one flop, you hit the output port. So we will report that as a RDC. We will not consider that it's a safe RDC because we are not able to skip the second flop. And we do preserve that in our HDM. When you will just utilize that HDM at the top level, the further analysis will happen, and accordingly, whether it's a safe RDC or an unsafe RDC will be reported. So in short, it is supported for both the flows, for flat as well as for hierarchical HDM based flow.
Okay, and one final question would be on even after applying a particular depth, if your violations still have destinations with resetless flops, does it mean to go ahead and then again increase depth, or is there another methodology for that? For why some of the destination flops are still found unreachable and reported process?
Yeah, very good question. So I think depth has to be decided upfront. You cannot take a call that even after skipping the 2 flops or 3 flops, I still hit another NRR. No, that is basically the design architect call. He has to take a decision upfront before doing the RDC analysis. And once the depth is decided as 2 or 3, whatever, then after skipping that many NRR flop, if you hit further NRR, it becomes a RDC problem, and that has to be fixed. You have to add a basically synchronizer or isolation signal to take care of that RDC. The methodology is not to increase the depth further, because what should be the right depth, that has to be decided upfront before RDC analysis.
Okay. Thank you, Atul. Thank you, Sai, for your time. I think I answered all the questions, and I don't see anything else on the chat window. Nice presentation. Thank you.
Thanks, Harsha.
Thanks, Harsha.
So with that, actually, it's a wrap on this session. I think further to that, we have poster sessions in line. Probably it can be continued, but on this session 3 of day 2, I think the track 3 comes to an end with this. Thank you all for attending.